Hey everyone, ready for another deep dive? Today we're going to be looking at how to make AI image and video generation crazy fast, like lightning fast, but without, losing any of that sweet, sweet quality.
Yeah, it's a challenge, right? Speed and quality.
Exactly, usually you get one or the other. But this research we're looking at, it's all about this really cool technique called parallelized autoregressive generation.
Whoa, mouthful. But don't let the name scare you.
Yeah, it sounds super complicated, but the idea is actually pretty simple.
It is. Think about how you'd write a sentence, right? You kind of predict the next word based on what came before it.
Like predictive text, right? My phone does that all the time.
Exactly, it's kind of like that. But instead of predicting words, we're predicting pixels or, those visual elements.
So it's like predictive text, but for pictures. That's pretty cool.
Yeah, like a superpowered version. But there's a catch.
Oh, there's always a catch. What is it?
Well, that whole prediction process, doing it one tiny element at a time, it could be super slow. Imagine a painter, right, trying to fill in every single pixel of a giant mural, like in order.
Oh, man. That would take forever.
Yeah, it would. And that's the problem this research is tackling, like head on.
So how'd they solve it? Did they just, get a faster painter?
No, not quite. The key here is that they realize not all those visual elements depend on each other equally.
Okay, so some are more important than others.
It's more like some have to be done in a certain order and others have more freedom. Think of a puzzle, right? Some pieces, got to put them in first. Others, a little more wiggle room.
Okay, that makes sense.
So what they figured out is that pixels that are far apart, they're often like weakly correlated.
So, knowing what color one brick is doesn't really tell you much about the color of a brick on the other side of the building?
Perfect analogy. So you can predict those distant pixels at the same time in parallel without, messing everything up.
Whoa, so you're telling me they found a way to predict multiple pixels at once? That's pretty wild. Did they test this out?
Oh, yeah, they did. They used it on ImageNet and UCF 101, which are those, massive data sets of
Yeah.
images and videos.
Right. I've heard of those.
And the results were seriously impressive. Imagine, like, generating images almost 10 times faster without losing any noticeable quality.
10 times faster? You're serious? That's a game changer, especially for someone like me who's, well, let's just say I'm not known for my patience.
Yeah, no more waiting around for those progress bars to fill up.
Exactly. So what kind of impact could this have on video creation? That's got to be huge,
Oh,
right?
absolutely. Think about it. If we can generate video that much faster, it could, like, totally revolutionize how we create and watch videos.
That's wild. So, artists and designers could have tools that just, boom, make these amazing videos in a fraction of the time.
Yeah, no more pulling all-nighters to meet deadlines.
Then what about, AI-powered video games? Or those, crazy realistic simulations?
Exactly. We could see those things become so responsive, so immersive.
Mm-hmm.
It'd be like, whoa.
Mind-blowing.
Yeah, and it could even impact sustainability. Make the whole process way more energy efficient.
Okay, so we're talking faster creation, better experiences, and it's better for the planet. I'm sold.
Yeah.
But wait, hold on. We're getting ahead of ourselves. Let's back up a bit. How does this whole two-stage strategy actually work? I mean, walk me through it.
Okay. So stage one, it's all about laying the foundation.
Okay, good foundation. Got it.
They generate a few key elements, like sequentially, kind of like those crucial puzzle pieces you got to put in first.
Right, like the corner pieces. You got to start somewhere.
Exactly. This sets up the basic structure of the image or video. Think of it like establishing the composition, the basic shapes and colors, the layout.
So it's like creating a blueprint for the AI to follow.
Yeah, you could say that. Then comes stage two. That's when things get really interesting.
Okay, stage two, lay it on me. What happens?
Well, that's where the magic of parallel processing really kicks in. The algorithm finds groups of pixels that are far apart. And since they're not, super connected, it can predict what they should look like all at the same time.
Whoa, that's where the speed boost comes from.
Yep, exactly.
But wait, wouldn't that just create a jumbled mess of pixels if they're all being predicted independently?
You'd think so, right? But that's where this thing called attention mechanisms comes in.
Attention mechanisms.
Yeah, it's how the model makes sure that all those parallel predictions, they have the right context and don't end up looking like, a random explosion of color.
So even though they're generating pixels in parallel, they're not working in complete isolation.
Exactly. It's like giving each pixel worker a cheat sheet so they can kind of peek at what everyone else is doing.
Uh-huh. That makes sense.
Keeps everything nice and coherent.
Okay. I think I'm starting to see the big picture here. They found a way to use parallel processing, but still make sure the final image or video looks, good.
Yeah, cohesive, high quality. Just a balancing act for sure.
So how did they pull it off? What kind of design choices did they make?
Well, one of the things they had to figure out was like the order in which they predicted those groups of pixels. In the traditional way, it's like one by one, like
Yep.
reading a book. But here, they needed a different approach.
Right, because just going randomly wouldn't work, would it? They had to find some logic, some way to avoid making the image look all messed up.
Exactly. And what they came up with is this strategy called region-based distant ordering.
Region-based what now?
Region-based distant ordering. It's a mouthful, I know. But basically, they divide the image into different regions and then generate the initial tokens in each region, like sequentially.
So it's like they're outlining the main parts of the image first before letting the algorithm loose on the details.
Yeah, kind of like that.
Okay, that makes sense. But how do they decide which pixels to group together for that parallel prediction?
That's where their understanding of those token dependencies comes in. Remember how we said some pixels are, like, more related than others?
Right, right.
Well, they use that knowledge to group together tokens that are far apart, because those are less likely to, like, mess each other up.
So they're being super strategic about which pixels they predict at the same time. It's like a carefully choreographed dance of pixel generation.
Ah, I like that. And they didn't just stop there. They also tried different parallel group sizes, like how many pixels can they predict at once without sacrificing quality?
Finding that sweet spot, huh? So what worked best?
They found that groups of 4 or 16 tokens worked best.
So not too big, not too small, just right.
Goldilocks zone of pixel prediction.
I love it. This is all starting to sound really complex. Did they have to, mess with those attention mechanisms, too, to make sure they were working right with this parallel approach?
Sure. Absolutely. They found that a specific type of attention called full attention was super important. It's like,
Yeah.
imagine each pixel worker. They've got this cheat sheet, and it shows them the whole mural, even the parts that are still, like, being painted.
Okay, so they can see the big picture, even if they're just working on a tiny part.
Exactly. And that helps them make sure their little piece fits in, keeps things from looking all weird.
I get it. So they're not just coloring in random pixels, they're making sure everything works together.
Right. And it really makes a difference when they compared it to, like, a more limited type of attention. The quality was way worse.
So full attention, that's the key.
It is. It is. Keeps everything looking nice and smooth, even with all that parallel stuff happening.
Okay, so they've got the blueprint stage, they're grouping those pixels strategically, and they're giving them these cheat sheets to keep everything in check. Sounds pretty thorough.
Yeah, they thought of everything. But, the real test is, did it actually work? Like, what were the results?
Right. Show me the numbers.
Well, remember those speed ups we were talking about? Like 10 times faster.
Yeah. Almost
Yeah.
too good to be true.
Well, they actually achieved that. And get this, without any noticeable drop in quality.
Hold on, you're telling me they generated images 10 times faster NND? They still looked amazing?
That's exactly what I'm saying.
Yeah.
Same level of detail, same realism.
Okay, but give me a real-world example. Like, what would that mean for, let's say, a video game designer?
Imagine you're working on this super complex scene, right? Instead of waiting like hours for the AI to generate it, you could see the results in minutes.
Oh, man. That would be a game changer, literally.
It would totally change how you work, how fast you could bring your ideas to life.
No more staring at loading screens. Sign me up. But, okay, what about video? I mean, that's got to be
Yeah.
way more complicated,
No,
right?
you're not wrong. Video is a whole other beast. But guess what? They apply this method to video generation too.
No way.
And the results were just as crazy. They saw speed ups of up to like 12.6 times faster.
12.6 times faster?
That's what I'm saying.
Okay, my mind is officially blown. But wait, did the video still look good? Like, I'm picturing all blurry and jumbled.
Nope. That's the amazing thing. Even with those crazy speed ups, the quality was still top notch. Smooth motion, realistic details, the whole shebang.
Okay, how did they even measure that? Like, how do you know if a video looks good?
Well, they use this thing called Frege video distance, or FVD.
Frege video what now?
It's basically a way to measure how similar the generated videos are to, real videos.
So the lower the score, the better? Like, the more realistic it looked?
You got it. And their scores were, like, practically the same as the slower methods. It's a huge breakthrough. They really decoupled speed and quality.
It's like they found the cheat code for AI video generation. You get the speed, A&D, the quality. Mind-blowing. Makes you wonder what else we could do if we just change how we approach these problems.
That's exactly what's so exciting about this, right? It challenges those assumptions, like you have to sacrifice quality for speed. It opens up so many possibilities. Imagine AI generating like these super realistic visuals in the blink of an eye.
Whoa, it's like the future of movies, video games, everything.
Right. And we could create new forms of art, those crazy realistic simulations for like training and education.
We could do it all way more sustainably. It's like they've handed us the keys to a whole new era of visual creation.
I know, it's
Yeah.
awesome. But before we get too carried away dreaming about the future, let's take a moment to appreciate just how clever this research is. They didn't just stumble onto this, you know. They had to really think about every little detail.
Yeah, it wasn't just luck. They had to make some smart choices along the way. So, what were some of those key decisions? What made this breakthrough possible?
Well, one of the first things they looked at was the importance of generating those initial tokens,
Hmm.
you know, the ones that set the foundation sequentially.
Right, right. They had to do those in order.
Exactly. And they wanted to see if they could like skip that step, generate them in parallel too.
So just let the AI loose from the start. I have a feeling that didn't go so well.
You'd be right. When they tried that, the results were, well, let's just say a disaster. The images were all jumbled up, like nothing made sense.
Yeah, makes sense. You need that foundation, that shared understanding before you can start adding details in parallel.
Right. Otherwise, it's just chaos.
So, lesson learned. Sequential generation for those initial tokens is a must. What else did they try?
Well, they also spent a lot of time figuring out the optimal parallel group size, you know, how many pixels to predict at the same time.
Right, right. Too few and it takes forever. Too many and it all goes haywire.
Exactly.
So what was the magic number?
They found that 4 or 16 tokens worked best.
Not too big, not too small. Just right.
Yep. The Goldilocks zone.
I love it. They're really fine-tuning this whole process. I bet those attention mechanisms also needed some tweaking, right?
Oh, absolutely. They had to make sure each pixel was getting the right info, even with all the parallel stuff going on.
Hmm.
They tried different attention patterns and found that full attention was the way to
Wow.
go.
Full attention? Huh. Sounds intense. What does that even mean in this context?
Well, you can think of it like this. With full attention, it's like each of those little pixel workers, they can see the whole mural, even the parts that are still being worked on.
So they have like a bird's eye view, even though they're just focusing on their own little section?
Exactly. Gives them the full context,
Yeah,
right?
right.
So they can make sure what they're doing fits in perfectly, even if they're working independently.
Ah, so it keeps everything from getting all wonky, smart.
Yeah, it's like they're all connected, you know, even though they're working on separate parts. It really helps create that like cohesive, realistic final image.
Okay, so they figured out that initial sequential stage is important. They optimized the parallel group size, and they fine-tuned those attention mechanisms. Anything else they had to, like, puzzle through in this whole parallelization thing?
Well, there's also the order in which they predict the tokens, even within those parallel groups.
Mm-hmm.
Might seem like a small thing, but it actually makes a big difference.
Yeah, because you wouldn't want to predict the color of a pixel in the middle of an object before you even know where the edges of the object are, right? That would just be a mess.
Exactly. Gotta have a strategy, you know, something that takes those dependencies into account.
So what'd they come up with?
They came up with this thing called region-based distant ordering. It's a bit of a mouthful, I know.
Region-based distant ordering. Try saying that 5 times fast.
Yeah, right. But the idea is to predict tokens in groups that are, like, far apart from each other.
Wait, so they're not just going like row by row, they're jumping around the image, predicting pixels that are miles apart.
You got it. And it makes sense when you think about those token dependencies, right? By predicting pixels that are far apart, they're less likely to, you know, step on each other's toes.
So it's like they're weaving the image together, making sure everything fits, even though they're not working in a straight line.
Yeah, it's pretty cool. They're minimizing the chances of getting those, like, weird artifacts or inconsistencies.
This is some next level pixel choreography.
I like that. I like that. And it really shows how much thought they put into this whole thing, right?
Yeah.
They didn't just force it. They were really careful and methodical about it.
Yeah, they really dug deep and came up with a solution that's both, like, elegant and effective.
It's a testament to the power of really understanding the problem, you know. They didn't just throw algorithms at it and hope for the best. They really thought it through.
It's inspiring, isn't it? It makes you realize we can achieve some pretty amazing things if we just, take the time to understand the fundamentals.
Absolutely.
Yeah.
And their work, it's not just about image and video generation. It has implications for other areas of AI too. If we can parallelize this, what else can we do? What other boundaries can we push?
That's the question, isn't it? what else are we missing because we're stuck in these old ways of thinking?
Exactly. This research is like a wake-up call, you know.
Yeah.
It's telling us to question assumptions, to look deeper, and to never stop exploring.
I'm definitely feeling inspired. This deep dive has been like a total mind-blowing experience. I've learned so much about AI. And, I'm walking away with this sense of like, wow, the future is going to be incredible.
I'm glad to hear that. That's what we'd love to do, you know, share these amazing breakthroughs and hopefully inspire others to like dive in and explore these ideas themselves.
Absolutely. And for anyone listening who wants to, really get into the weeds of this research, we'll have a link to the paper in the episode description. It's definitely worth a read if you want to see how they actually pulled this off.
Yeah, go check it out.
And as always, keep exploring, keep questioning, and keep pushing those boundaries. Who knows what other incredible discoveries are out there waiting to be found?
That's what makes it all so exciting, right? The possibilities are endless.
Well, that's it for our deep dive today, everyone. Thanks for joining us.
Until next time, stay curious.